In this video series, we're going to look at building .NET 6 microservices from scratch and deploying them to the cloud using AWS Fargate. Hey everyone, Wes here. I hope you're doing well. I'm really excited about this series because we're going to dive into the topic of microservices architectures. And we're going to be building .NET services from scratch, deploying them as microservices to AWS, and talking about all the considerations of microservices along the way. I think a hands-on approach at a really simple architecture, a really simple application is a great way to get started in understanding how microservices work at a really sort of mechanical level. But I do want to acknowledge the fact that although the term microservices is really hyped right now, it's a really sort of popular architectural pattern, it comes with a number of trade-offs. And so we're going to be talking about those trade-offs, the trade-offs between a traditional monolithic style architecture on one hand with a microservices style architecture on the other. They each have their own pros and cons, and it's often the case that for very simple applications, a monolith just makes a lot of sense. For very large, complex organizations and large, complex pieces of software, we often see the monolithic style architectures being a bottleneck to releasing features, to deploying rapidly. And so we'll talk about the ways that microservices architectures really support those particular types of business needs that occur as software grows and becomes more complex. The real core benefit of microservices, I think, is the independent deployability of each different piece of software that comprises your entire application stack, or maybe all the software that your business delivers. And so this idea of independent deployability is going to come up again and again as we talk about the decisions that we make when we build microservices architectures. This idea that we have to deploy the entire software as a single unit anytime a new feature is introduced is something that is just the case with monolithic style architectures. Microservices are inherently distributed systems. So whereas in a monolith that we may have sort of more than one moving piece, we may have communication over a network in the form of database connections or other derived data sources like caches and maybe search indices. A monolithic application, on the other hand, is inherently decoupled, inherently distributed. There are going to be many more sort of network endpoints, and communication is going to be happening more often than not over a distributed network as opposed to within a single process or running on a single host. So this introduces a lot of complexity. I hope to sort of begin to address some of that complexity in this series. But the main focus here is going to be talking about a hands-on approach to building microservices in .NET and deploying them to AWS. AWS Fargate actually makes the deployment and orchestration of our containerized workloads actually quite simple, to be frank. It is a sort of serverless approach where AWS will basically handle the provisioning and management of all of the underlying compute infrastructure. So as operations, we don't need to worry about provisioning individual VMs via EC2 or something, and installing Docker and installing other sort of configuration or orchestration tooling on those nodes. Instead, in using Fargate, we're simply going to define several tasks and container definitions, if you will. We're going to push Dockerized images up to Amazon ECR, the Elastic Container Registry, and then ECS is going to use those images to execute our containerized workloads across compute that it manages, and we don't really need to worry about the underlying infrastructure. We're going to get into all that. Clearly, there's a lot to cover in this series. I'm really excited about it. We're going to look at an example application, which is essentially a weather report application. The idea being that as users, we would like to make a request to this software, providing it with our zip code and some time span, and the software is going to look into various data sources to return to us this sort of aggregate which represents a weather report for a particular location over some historical record, some period in the past. And so to that end, we're going to have microservices for precipitation and temperature records, and then we're going to have a microservice for the weather report itself, which collaborates with those other services to provide a user with a report. Now, this collaboration is going to happen over a synchronous protocol, HTTP. It's very popular, of course, and very common. There are other ways that microservices communicate. Of course, there are many asynchronous messaging protocols. When we talk about things like message queues with the AMQP protocol. Amazon SQS is another example of a message queue that in this case is hosted in the cloud. There are event streams that we could use. We could talk about using Kafka for microservices, collaboration, communication. But in this video, we're going to stick with HTTP. It's very well understood. But note that just among the many other sort of decisions that we need to make as architects when we're designing these types of microservices applications, just something else to keep in mind is the messaging protocol and the pros and cons of synchronous versus asynchronous communication. There are many other things to cover here, lots of interesting topics about failure modes, distributed transactions, all of the failure modes associated with distributed systems, service discovery, the list just goes on. So I think the best way to get started here is just to dive in. We're going to take a look at a diagram, and then we're going to work step by step, and we're going to take a look at the development, the infrastructure provisioning, and the deployment of our workload to AWS using ECS Fargate. So thanks for watching. Be sure to like and subscribe. If you get anything out of this video, I'd really appreciate it. And know that patrons of the channel via Patreon get full access to all the source code for this and all the projects on the channel. Thanks for your support and thanks for watching. Let's dive into our microservices architecture in .NET. Okay, so let's take a look at a high-level diagram of the software that we'll actually be building throughout this series. So let's take this first from a sort of user story perspective, in that as users, what we're trying to achieve here is we would like to be able to make an HTTP request to some software, and we're going to provide that software with our zip code and then some number of days in the past where we want to retrieve some historical weather data in the form of a weather report. And so we're going to essentially build the software that fulfills that particular user story, and we're going to take a microservices architecture approach to actually solving this problem. Now, what we have here is a very simple microservices architecture. We've got three services that are sort of collaborating to build and provide a user with this weather report. So we'll be building three separate microservices in .NET, a weather report service, a precipitation service, and a temperature service. We're also going to be building a simple process in the form of just a basic console application that will be making post requests to our temperature and precipitation services to actually seed data for our software. So this is going to provide us with some test data that we can use for things like end-to-end testing or integration testing, and in our purposes just to have some data to play with while we build out this particular piece of software. So a few things to note here. Each service will contain its own data. It's going to use its own separate database, and this is a really important consideration when dealing with microservices. We typically want every service to essentially control its own data. And so we'll have this database per service pattern that we'll be using. And really the driving motivation for that is that one of the core benefits of a microservices architecture is the ability to independently deploy any given service. If we can't independently deploy any service, then we already lose much of the benefit of working with microservices. So we can imagine that if our application is growing and we have maybe a standard setup where we have, say, a dozen or even up to several hundred microservices, then we'll be working with an organization that has multiple software development teams. And in those cases, it's going to be really crucial for individual teams to be able to take full ownership of the microservices that they're working on and not really need to collaborate so much across teams who are dealing with different services. So, for instance, if I'm working on a team that's building out the temperature service, then it's going to be really beneficial to myself as a developer and to my team to be able to essentially control the deployment, control the cadence with which we deploy our service, control the data access layer itself without really having to worry about the human communication and collaboration with other teams that are responsible for other parts of the system. So often in microservices architectures, we'll see services that are split by business domains. This is very common. And this is so that each domain, each particular part of the business can really own the business logic for that aspect of the business. And as we need to sort of work across seams, we need to sort of agree upon really nice and stable contracts. That way, the services that are collaborating with the piece of software that we're working on essentially have this definition of how to communicate with us, what type of response to expect in return, and it's really our job to sort of uphold that contract and to control the implementation details within our team. So that's a long way of saying, one of the core motivations for microservices is this concept of independent deployability, and to that end, we'll have a separate database per service. Now, another thing to note here is you can see that the way that services are communicating with each other is over HTTP. So HTTP is a synchronous messaging protocol, meaning that when we make a request, we're going to be waiting for a response. Essentially, we can't do anything in the meantime with the data that we're requesting, obviously, until we have it back. And so this is a synchronous way for services to communicate. In many other situations, you'll also see microservices communicating over an asynchronous messaging protocol, something like AMQP in the case of message queues with something like RabbitMQ, or similar protocols that might be implemented by something like Amazon SQS. There are also very popular event streams like Kafka, which could be used for inter-process communication in a microservices architecture. In our case, we're going to be using something that's very standard, it's very well known, very well understood, which is HTTP. It just so happens that HTTP is a synchronous messaging protocol, and so we need to take into consideration what that means for our overall design when we make this decision. Now, we have a very simple setup, a setup that hopefully just gives you a sense of the mechanics of the way that microservices operate and ultimately the way they can be deployed, in this case on AWS. But we'll need to think about all of the complexities that having a microservices architecture introduces into our software development as opposed to a traditional monolithic application. So everywhere we have arrows here in this diagram is a potential point of failure. These are services which are going to be running typically on different hosts, meaning they could be running in different geographic locations. Certainly they will often be running on different underlying compute resources, different VMs, different hardware. And as you may imagine, there is a lot of complexity in sort of understanding how these types of systems communicate, but also how they fail. And so we'll have to take into consideration what happens when weather report service makes a request to precipitation service and temperature service to collect some data, and say temperature service doesn't respond for whatever reason. And that could be because of a hardware or a software failure. It could be some problem with the network, some problem with configuration. So these are all things that we need to be considering when we decide to take on the additional complexity at the benefit of being able to have independent deployability and sort of separation of business concern by separate service. Okay, so that's kind of a high-level diagram here. As mentioned, the services will be developed in .NET 6. We'll be using a Postgres database as a backing database for each of our services. We'll only need to spin up one database server, and we'll look at how to create separate Postgres databases on that single server, both locally and orchestrated using Docker Compose locally, but then RDS when we're talking about deploying into AWS. And then the services, of course, will be containerized, and we'll look at how we actually deliver those containers to a container repository or container registry in a moment. So we're going to be deploying these services to a staging environment that we'll set up from scratch in AWS. So this diagram is helping us understand that as developers, we're going to be containerizing the work that we're doing and essentially pushing images, tagged images, up to Amazon ECR, which is our container registry. If you haven't used ECR before, you can think of this as something very similar to Docker Hub, where we can have private repositories for our organization where we build and tag Docker images and then push them to the store, where they can then be referenced by any of the other resources that want to run those workloads in our little piece of AWS, in this case in a VPC. So we're going to create a VPC, and then from within this VPC, we're going to provision a new ECS cluster. So we're going to be using Amazon ECS to orchestrate our services. And I realize that if this is your first time sort of orchestrating containers in the cloud, there can be kind of an overload of concepts and vocabulary here. But as we work through this step by step, I think you'll see, in fact, how simple it is to get a small number of microservices like this set up very quickly. So within our ECS cluster, we're going to essentially create what ECS calls task definitions. These task definitions will essentially say, hey, give me this particular Docker image that's referenced in Amazon ECR, and we're going to run this as a Fargate task using an ECS service. So there are a number of different ways to orchestrate containers and to set up these task definitions in ECR. We're going to be using ECS in ECS. We're going to be using ECS Fargate, which is a fantastic solution that AWS has provided that basically allows us to not worry so much about the underlying compute infrastructure. So we won't need to be provisioning our own EC2 instances to run as virtual machines that will basically have Docker installed and host the containers that are running. Fargate is just basically going to be this sort of layer of abstraction that AWS is providing that says, hey, AWS will manage the underlying compute infrastructure. You just define how much compute you need. You define environment variables, different things that you would like to actually set up in terms of networking and where your images are coming from. And AWS via Fargate will sort of make sure that those containers can be placed with the amount of resources and the networking that you've configured. And so to that end, we're going to be running our 3 services on Fargate: Precipitation, Temperature, and Weather Service. And again, the naming can be a bit confusing here, but ECS has this concept of services which are meant for running these task definitions in sort of a long-running continuous context. So if these services fail, ECS can ensure that new instances of containers are provisioned, and so that our services are running with the availability that we need at any given point in time. And then we'll also look at how to run our data loader, which is just a simple console application, not really a microservice. We can also run that as an ECS Fargate task as opposed to this long-running service. So we can just have that triggered, in this case, manually. Okay, so we're going to walk through all of this step by step. We're actually going to write the code from scratch. We're going to build out the .NET solution. We're going to push it to version control. We're going to containerize our applications. We're going to push those container images up to Amazon ECR. We're going to provision an ECS cluster and run each of our containers using ECS Fargate. And so we have a lot to work through here, but I hope that this is a great introduction for you to a microservices architecture, developing microservices in .NET 6 and deploying .NET to AWS. So with that, let's go ahead and jump into some code and we'll get started on our .NET 6 solution. Okay, so the first thing that I'm going to do here is I've just created a project directory called Microservices Weather. We can see that this is a completely empty directory, and so we're going to create a new .NET solution. For that, we can use the command .NET new sln. And if we take a look here, we now have a microservices-weather.sln file. Now we're going to create 4 separate projects here. We're going to create 3 microservices for precipitation, temperature, and our weather report service, and then we're going to create a 4th application, which will just be a simple console application to populate data into our temperature and our precipitation databases. So let's go ahead and do that now. So first we'll run .NET new web API-o cloudweather.precipitation. This is going to create a new .NET 6 web API project in a directory called cloudweather.precipitation. We'll do the same thing for a temperature service and a report service. Okay, so if we take a look now, we have those 3 subdirectories, one for each of our 3 microservices. Then we're going to actually create a data loader service, which won't be a web API, but will rather be just a bare bones console application. Okay, so if we take a look at our directory structure now, we have those 4 subdirectories at the same level as our solution file. Each of these subdirectories is a separate C# project and therefore has a CS_proj file. Now, in order to associate each of the projects with our single .NET solution, we need to add them to the solution. We can do that with a single command here by saying .NET sln add and then a glob pattern here to pick up all of the CS_proj files in our subdirectories. Okay, with that, basically our solution is now set up, so let's open it up in Visual Studio. Okay, so here we are in Visual Studio, and we can see that our solution does indeed include our 4 separate C# projects. And we can see that the Cloud Weather Data Loader is a simple console application that simply writes out hello world. So of course we'll be modifying that shortly. And then each of our 3 web API projects has quite a bit of scaffolded code, including a controllers directory and a weather forecast object in each of these. What we'll do first is actually we don't need any of this, so we're going to delete the controllers directory from each of these projects. We're also in fact going to delete the weather forecast file in each of them. So it just so happens that the .NET CLI, when it scaffolds out a new web API project, creates this weather forecast application, which is somewhat similar to what we'll be building, but we won't reuse any of it that is provided for us in this case. Okay, so then let's take a look in our Precipitation project at our program.cs. So we can see that this is in fact what's called a minimal .NET 6 web API, which is a sort of new paradigm that .NET has provided as far as new things that are in .NET 6. We're going to even actually make it more minimal than it is here. We're going to remove services.add_controllers. We're going to remove the endpoints API Explorer and Swagger. And we're going to remove Swagger from this section as well. We're going to remove HTTPS redirection, authorization, and mapping controllers. So what's left is essentially 3 lines of code that creates a new web application builder, invokes build on that instance to create a new instance of a web application, and then invokes run on that web application to actually start our web API. And so you can see just how minimal this is and just how little code is really required in .NET now to get a running web API. So we're going to basically copy this code into the other 2 program.cs files for both the Cloud Weather Report and Cloud Weather Temperature here. Okay, the next thing that I want to do is just to note that each of our projects contains an app_settings.json file, each of our web API projects. Now this is sort of the canonical way to configure .NET applications out of the box. Often you'll see app_settings.environment.json, so for instance development.json, staging, production.json. We're actually going to be using app_settings.json only when developing locally. When we deploy our applications to the cloud, we're going to pass environment variables at runtime to actually configure the code that's running in our containers. And so I prefer to use environment variables rather than app_settings.json in general. But for working locally, app_settings.json is going to work very well for us. And in fact, we'll see how environment variables and this JSON notation sort of map one-to-one with each other using a special syntax in the environment variables. We'll take a look at that a bit later. Okay, in the properties directory of each of our microservices, we have a launch settings.json. Now, what I'm going to do here is we're simply going to modify the application URL to be a different port value. So we're in our Precipitation service on HTTPS. Let's listen on port 4001, and we'll listen on port 4000 over HTTP. For launch URL here, we're just going to remove this. We're not going to open up to a specific URL. And in fact, we can even remove launch browser. That should be fine. Okay, then we're going to open up properties in our temperature project, launch settings.json. Again, I'm going to remove launch browser and launch URL. And for temperature here, let's run this on HTTPS localhost 3001 and HTTP port 3000. And then finally, let's open up our properties for our weather report here. And we'll run the weather report on HTTP 5001 and localhost 5000. We'll go ahead and remove the launch URL and launch browser again. And so what this means is that when we're running our application from the debugger here in Visual Studio, each of our services will get a controlled port that they're running on, and there won't be any port sort of overlapping with any others. And so that's going to be very useful for us when we're running all on the same host, in this case localhost. Note that when we're deploying microservices to a typical production environment in the cloud or even on-prem, often we'll be running our services on different hosts, and we need a way to sort of network them together so that, of course, they can communicate with each other. In our case, when we're going to deploy to AWS, we'll see that we'll in fact run our microservices all on the same port, but they'll be deployed to separate hosts which are defined by different internal IP addresses. This is also a place where we could bring up the topic of service discovery, which is the idea that we want a way to resolve the host and the port where services are deployed dynamically, really without having to manually configure a lot of the underlying values, the host values and the port values for our services, because those could change very frequently and often do change very frequently. And so we could set up a service discovery platform which would essentially keep a registry of where services are deployed, and then any orchestration framework that needs to sort of orchestrate the services that are running together can refer to the service registry as to where individual services are deployed. It's a little bit more of an advanced concept with microservices, but you should at least be aware of the concept of service discovery and how it relates to deployment particularly. Okay, so let's go ahead and build now and make sure that we're building. Okay, it looks like everything's building. So what I'd like to do now is just to set up a new Git repository, so we can git init to create a new repository locally. And then in your editor of choice, we're going to go ahead and create a .gitignore file. To this, I'm going to add .vs, which is a hidden directory created by Visual Studio that we don't need in version control. And we're also going to ignore any directories that contain build artifacts, which in the case of .NET here are the obj directories and binary directories. So we don't need those in version control. Now I've set up a GitHub repository here that we're going to push code to. And I want to send a huge thanks and a shout out to patrons of the channel who support the channel via Patreon. As a patron, you get access to all of the source code in the private repositories, including this project and any other project that I create on the Productive Dev YouTube channel. So I'm sincerely grateful for your support. And if you would like access, then please consider becoming a patron of the channel. Of course, these YouTube videos will always be free to watch, and so feel free to code along with me. But if you'd like access to the source code itself, then it is available to patrons of the channel. So thanks for your support. All right, so what we're going to do now is essentially make our first commit. So we can add here, and we'll commit, saying initial commit. Okay, and then we're going to change the name of the branch to main. And then we need to add our remote. So let's go ahead and do that. And then we'll git push u origin main.